Monte Carlo Tree Search, thinking about terminal states. Last tutorial, we took a look at the Monte Carlo Tree Search algorithm in depth. Tree traversal, rollout, expansion, and backpropagation were discussed. The algorithm graph was shown and a very basic example was demonstrated. If you have not watched the previous tutorial, please do so before watching this one, as I will not be explaining things as in-depth as a previous video. I will assume you've known about the algorithm or have watched the video in order to proceed with this video. For example, when we discuss the UCB scores in this video, I will just show or say the answer instead of showing how the algorithm is processed. However, the UCB formula will be shown on the screen just like last time for reference. Let's simplify things for a real-life example. Let's take a scenario where we have two game entities, a human-controlled object known as a player and a computer-controlled object known as the enemy. We want to connect the AI to the computer's decisions. This scenario has the player having 97 health out of 100 and the enemy having 8 health. The available actions are to either attack, which deals between 10 and 11 damage, or to heal, which restores between 12 and 13 health. An algorithm should be able to take this scenario and instruct the enemy which action would be best to perform. We can tell just from looking at the attributes of both objects that the enemy should heal. To make this algorithm work properly, we need to specify scores and terminating states. A terminating state is when the game can no longer proceed. In the previous tutorial, it was demonstrated that the action that produced the highest score child was chosen. Therefore, we want to properly weight the scores of the terminating states. The terminating states that will be used for these examples are the player dies, which produces a score of 50. The enemy dies, which produces a score of -1. Neither of these produces a score of 0. Okay, let's take a minute here to discuss the scores of the last two. Monte Carlo Tree Search is based on limitations. In a fast-paced situation like a video game, we do not want this algorithm to take a long time. Therefore, we need to specify a cutoff time. If the algorithm is in the middle of a rollout, this can occur. Therefore, if a stalemate is to occur where the player and the enemy are still alive, a score of 0 is provided. This situation is in the enemy's point of view. The enemy would absolutely prefer a stalemate over dying. Therefore, a score of -1 is generated to be less than the stalemate. Okay, there is a problem with these terminal states. The way the terminal states are listed will not result in a proper algorithm. Let's run through a few iterations to see why. We will not be dealing with any cooldowns or long abilities for this example. It will be enemy action, player action, enemy action, and so on. It'll go back and forth. The algorithm takes the initial state of player health of 97 and enemy health of 8. We first generate the direct children for this state with the provided actions. State S1 has the player health at 87 because it's the hit action, and the enemy health at 8. State S2 has the player health at 97 and the enemy health at 20 due to being the heal action. We choose the first child node and perform a rollout which produces a value of -1 for the enemy dying. Enemy has 8 health, and it takes 1 hit from the player. Backpropagation is performed, tree traversal occurs, but since state S2 has 0 visits, S2 is chosen. Rollout is performed and the enemy dies again, resulting in a score of -1. Backpropagation occurs, then tree traversal. Both S1 and S2 have a UCB1 value of 0.6651 since they both had the same scores, visits, and parent node. State S1 is chosen simply by order of children. Expansion occurs. This time, it's the player's turn. State S3 is generated with the player's health set to 87 and the enemy's health set to 0 due to being a hit action from the player's perspective. State S4 is generated with the player health set to 100 and the enemy health set to 8 due to being a heal from the player's perspective. The first child node is chosen, S3, for a rollout. Enemy is already dead in this state, so a value of -1 is produced and is back propagated. Tree traversal occurs. S1 has a UCB1 score of 0.4823 and S2 has a UCB1 score of 1.0962. S2 is chosen for the higher UCB1 score. Expansion occurs, again, which is the player's perspective based on the level of the tree. State S5 is generated with the player health of 97 and the enemy health set to 9 due to being a hit action from the player's perspective. S6 is generated with the player's health of 100 and the enemy health of 20 due to being a heal action from the player. The first new child node is chosen, S5. Rollout is performed, the enemy dies in 1 hit, so a score of -1 is produced and back propagated. Problem, hold up, something is not working properly. Let's take a step back. Now, both states S1 and S2 now have a same score and visits. If we were to stop now, due to running out of time, for example, what would be chosen as the best action? It would be hit. Due to the order of children, since it's the same score, same number of visits, S1 is the first child, so that is chosen as the best action. Something is not correct with our terminal states, and we need to revisit them. Okay. To help us understand how to think about this solution, let's ask ourselves why the enemy should heal in this provided scenario. Comparing the attributes of the objects, we know immediately that the enemy should heal. But why? To convert this into a proper algorithm, we need to think why and come up with a detailed reason. Given the scenario provided, the enemy has a very small amount of health to the point where the player will almost always win. So why should the enemy heal? The simple reason is to survive longer. Not just to increase its hit points, but to survive longer. From the enemy's perspective, surviving longer is preferred. After all, the player can make a series of mistakes that could lead to a much better scenario for the enemy. The scenario could potentially reverse if the player makes enough bad decisions. A simple way of calculating this as a score is to convert how many actions took place in the rollout phase. Okay, so we have new terminating states that are the following. The player dies, which produces a score of 50. The enemy dies, which produces a score of -1 plus how many actions took place. And neither of these produces a score of 0. Please note, for the sake of simplicity of this video, the enemy dying was simplified to be a simple addition. It would be preferred to not go into the positives by implementing a proper algorithm for actions that are still in the negative numbers. For example, if the enemy dies in one action, a score of negative 100 is produced. If the enemy dies in 70 actions, a score of negative 1 is produced. As the number of actions approaches infinity, the score approaches 0, but not becoming positive. Now, let's perform the algorithm with a second attempt. The algorithm takes the initial state of the player health being 97 and the enemy health being 8. We first generate the direct children for the state with the provided actions. State S1 has the player health of 87 and the enemy health of 8 due to being the hit action. State S2 has the player health at 97 and the enemy health at 20 due to being the heal action. We choose the first child node and perform a rollout. The player's turn is the first in their rollout, hit is performed, and the enemy dies. Terminating state says the score is negative 1 plus the number of actions that occurred. The enemy died in one action, so the rollout score is 0, which is backpropagated. State S2 is chosen since the visit count is 0. A rollout is performed. The player hit the enemy with max damage of 11, resulting in the enemy health at 9. The enemy hits the player, resulting in the player's health of 87. The player hits the enemy, which results in the health of 0. Enemy is dead. 3 actions took place. Negative 1 plus 3 is 2. Rollout value of 2 is produced, which is backpropagated. Tree traversal occurs and S1 has a UCB1 score of 1.6651 and S2 has a UCB1 score of 3.6651. S2 is chosen for the higher UCB1 score. Expansion occurs, which is now in the player's perspective. State S3 has a player health at 97 and enemy health at 10, and State S4 has a player health at 100 and the enemy health at 20. S3 is chosen for a rollout. Enemy goes first during the rollout phase this time, since it's the player's perspective. Enemy hits the player, resulting in the player health being 87. The player hits the enemy, resulting in the enemy dying. 2 actions took place, so the rollout value is 1 and is backpropagated. Tree traversal occurs. S1 has a UCB1 score of 2.0962, and S2 has a UCB1 score of 2.9823. S2 is chosen. Now let's go ahead and stop here. It's certainly better. We would have now visited S2 3 times if we were to continue, while S1 was still only visited once. S2 now has a score of 3. So if we were to stop here, if we gave it a certain length of time and now it's reached the limit, heal is now chosen as the best action. It is important to take a step back and really think about these terminating states. As shown in our first attempt, it appeared to be fine giving a score of negative 1 for the enemy dying. It made sense. However, we quickly saw how flawed this terminating state was with the provided example. And you can even extend on this new example, the new terminating state, and make it even better if you want. So, how can you test your own game state and terminating states? We will actually be implementing a Monte Carlo Tree Search in code in the next series of videos. We will also be implementing a test program where you can make sure the algorithm is working properly and your terminating states have the correct values. Now, it is important to keep in mind you want to have a good balance of how long the algorithm takes. What happens if it stops preemptively due to a time constraint? How do you appropriately handle your terminating states under these restrictions? If you're building a fast-paced game where you need a response time about around the average human reaction time, you want to think about these terminating states a little more differently than if you were to create a longer turn-based strategy game where you allow the computer to take maybe 30 seconds or a minute to think about their actions. There are a few games that have this kind of time, the length of time that it gives the computer to think. So it depends on your game, your architecture, what type of environment you want. All these things play into what type of terminating state you give, what points you give, how quickly the algorithm should run, what happens if it reaches a time constraint, how is that being chosen, and so on and so on. So this tutorial was just to give a real-life example, a limited real-life example. This is something I extracted from my current game project, and it was very simplified. I have way more than 2 actions that can take place, but for the sake of simplicity for the video, we only chose 2 actions, and there's more in-depth like shields and hull and all that stuff, not just health and player health and enemy health to deal with. Now, another thing to keep in mind is to remember Monte Carlo Tree Search is a random playout of the game, which means, and you can test this when you get your hands on the test project or implement it from our videos. This scenario that I just described, if I run it 100,000 times, I will get maybe about 10,000 of those will be choosing the hit action just by randomness. I might hit the player and the player might heal, or I might hit the player heals, I hit the player heals, and it goes on and on and on and on, and then eventually it switches to the player hitting me and I die. But that might have been 20, 30 actions. So there's an element of randomness in this. Alright, that's it for this video. I hope you enjoyed it. Stay tuned for the next video. I will just go over the code a little bit, and we will actually implement the code in the video. So thank you for watching this video. I hope you enjoyed it, and stay tuned for the next one.